Imagine we have square here, which is this side is x and the other side is x. The area of the square is about x squared. Now the question is, what if x squared is equals to minus 1? And how we describe about area is equals to negative 1. This leads us to imaginary region. The x squared equals to minus 1 before. If we take square root for both sides, we will get square root of minus 1, which I denote as I or imaginary number. To be specific, the x is plus or minus I. So if we have z as like this, which is a here is real, b is real number, then z here is about complex number, which being main focus in complex analysis. Now the question is, how about infinite series for f of z? The answer is, it stays the same but different in convergent tests and input and output. For example, take e power of x, which is about transcendental function or known as Euler exponent function here, which e here we get from this limit, which tell us why it's transcendental. And by this e definition, we will get e power of x here have the first derivative equals to itself. So if I expand this ex to power series, we will get this series expansion in Maclaurin series, which here is AK. We can input x as complex number too with different input and output. Then let z is equals to ix, which x is a real number, so we get this expansion. And by characteristic of I, we get this pattern. So by splitting even and odd order in series expansion, we will get this result, known as Euler identity, relate exponent to trigonometry, which means we can define that complex number is in complex plane, or known as Argand diagram. So now, if we have the function of z which can be expanded as power series, if we take z0 here, then we will get a circle like this as convergence region in complex plane. This part is real and this part is for imaginary part. So if we have z is equals to a plus ib as before, then b is here and a is here, which dot to this point. And that's it.